since the 1/4 is less than 1, that's a vertical compression. And again, by a factor of. We're going to see, as we look at the couple graphs that we do today, we're going to see those stretches and compressions in action. They're very visible with these types of functions, whereas the square roots and stuff that we did before, the absolute values they did before, we had to kind of like think of an analogy to work with that. And we said, oh, we're stretching that silly putty, and so we saw that as we stretched the silly putty up, that the parabolas tended to get skinnier, right? Or as we pressed the silly putty down, that the parabolas tend to get wider. Well, we're not going to see that same widening or narrowing effect today because the graphs look different. We're actually going to see that they look shorter, or they look compressed, or they actually look stretched vertically. So just the format of the graphs is different, so they actually act more visually like the way we would think they would. So we're going to start off by looking at the parent functions, like we usually do. So just the parent function for the square root function family is just f of x equals the square root of x. And so, we want to pick some x values here to plug in. We want to pick some, and see what y values come out. But we want to think about like numbers that would be easy to plug in, right? And numbers that are possible to plug in. So, think about what it means to square root something. And we know about square rooting. We've talked about that quite a bit. We can't square root negatives and get real answers. Okay, so we can't plot I and stuff like that here. So we don't want to use negative x values. So the most simple square root would be 0. Of course, the square root of 0 is 0. The next one would be 1. Square root of 1 is 1. Then 4 is a perfect square, and 9 is a perfect square. So all I'm picking here are perfect squares. Okay. That's the reason I picked those. There's nothing wrong with plugging in 8 or plugging in 5 or something like that, but you're just going to get a decimal answer, so it just kind of makes it a pain. So go ahead and plot those points: 0, 0, 1, 1, 4, 2, 9, 3. And because there are no values that we plug in below 0, because we can't plug in those negatives, there is no arrow to the left. Okay, there will be an arrow off to the right. This is a very flat curve as we go to draw it. So, but it does need to be a curve. Most of the curving happens right around the origin, so as you head off to the right, it's pretty flat. That does. It's not very good. So as I start at that point, the origin curving away from there through those points. Yeah, it's okay. Not my best work, but so I do want an arrow on the right end. And there's no arrow on the left end. Think about what domain and range mean, right? Domain is our x values. What x values can we plug in? Or the other way to think about it is if we come out from that left side, what's the first place we hit? First place we hit is at 0, and then it goes to the right forever. Because we are hitting 0, I want to go ahead and give that a bracket and a parenthesis on the infinity. So we can plug in numbers that are 0 or bigger. Then range, what y values come out. Okay. So again, we go left to right for domain, low to high for range. So the lowest place I hit is 0 again, and then it goes up forever. And bracket on the 0 because we're hitting that point, and then the parenthesis on the arrow on the infinity because we can't hit infinity. Okay? So left to right, low to high, we're doing domain range. I do want to talk about just another function real quick. This is not a parent function, okay, but it's just that reflection. I just want to show you guys that real quick. So if I were to do that, we just take all those y values and just give them negatives. So instead of 0, it'd be -0, which of course doesn't exist. -1, -2, -3. So the points would start at 0, 0, and then they just do this. Dotting that just to kind of separate them. Okay. But what reason I wanted to show you guys this is that look at that left end, right? So it still starts at 0 and goes to the right forever. So its domain is still 0 infinity, okay? But its range, this is really the reason I wanted you guys to see this. So as we come from the low side, the first thing I would hit, as we could start at the bottom, would be that arrow. Then it would go up and stop at 0. So its range gets flipped around. Okay. So just wanted you guys to see how that worked with the, so the domain didn't change. We're still plugging in those same x values, but we're getting different y values out. So the range gets flipped down. If you look at it now, this graph should look like a parabola that we have both sides graphed. It should look like a parabola, like x squared. So there's a relationship between the square and the square root graph, especially when you have both positive and negative square root graphed. You can see that parabola on its side now. So that is not the parent function, but I just wanted you guys to see what happens when we reflect it. Not something that we have planned out to talk about later. But anything there's square root wise you guys want to talk about? Anybody need more time there? Okay. Thanks, Jonathan. All right. The other parent function is for a different family. It's the cube root function. That's just f of x equals the cube root of x. So kind of the same way we did with the square roots. One thing about like what numbers we can plug in easily, and just think that there is a difference between square rooting something and cube rooting something, because we are looking for a number that multiplies by itself 3 times. We can cube root negatives, so we'll see a graph on both sides of the y-axis now. But the easiest number to cube root would be 0. That would be in the middle. Of course, cube root of 0 is 0. 1 also has a nice easy cube root. Cube root of 1 is 1. And then 8 is the next lowest cube root. The cube root of 8 is 2. So you guys got that roots chart last week or a week before, I can't remember, but just kind of remembering those first couple of roots. And then you can also cube root -1 and get -1, and cube root -8 and get -2. Okay? So 0, 1, and 2, 0, 1, and 8 are your perfect cubes, and then you have the -1 and -8. So again, I picked these numbers because they're perfect cubes. So those would be the points that I'm going to plot. 0, 0, 1, 1. 8, 2. And then -1, -1, and -8, -2. So we have a very flat curve here. Most of the actual curving happens right there around the origin again. The rest of it's pretty flat. This one looks more like an S though than the other one. Right. Since I go to draw that, There we see, oops. There we see a curve through there. Arrows on both ends. Should continue to gently slope up at the ends, and both ends, slope down at the other end. So it should look like a really stretched out S. Domain, right? There's an arrow on both ends, so that's our all real numbers. So negative infinity to positive infinity, left to right. Range goes down forever, goes up forever. So what's nice about that is that if that's always like, it's going to be always like that. It's always going to go left and right forever. It's always going to go up and down forever. No matter what we do to it, that's always going to happen. Okay? So domain and range for cube roots is actually really easy.
When you're done with this, you go to the one above real quick.
So, no matter if we reflect it, no matter if we stretch it, no matter if we shift it left or right, up and down, like the domain and range for a cube root will always be that. So makes that pretty simple. The square root one will shift around, especially when we start doing shifts and stuff like that. But we saw how the reflection changed the range. But when we're doing like the shifts tomorrow, we'll see how those numbers will change a little bit. But what you need, Jet? Do you get what you need, Jet?
Yes, I did.
Okay. All right. Anybody anything here on the cube root one? All right. Again, you guys have talked about reflections and stretches and shrinks. Again, compression, another way of saying shrink, multiple times. So that really shouldn't be a big surprise what's going on here. So just what does it look like if we do a vertical reflection? If our parent function was square root, then our just be negative square root. It's not that big a deal, Peyton. Like you guys have done this so many times that really you may not need to. If the parent function was cube root, then the reflected version of that would just be negative cube root. Right? If your parent function here for vertical stretch was square root, then maybe it's like 4 times the square root of x would be a vertical stretch. If the parent function was cube root, maybe maybe it's negative 2 cube root of x. There really should be a little absolute value signs here. So if the absolute value of a is greater than 1, right? So, like I said earlier, like this negative and the 2 do 2 separate things, right? The negative's job is to reflect, the 2's job is to do the stretching. So even though it's a negative 2, that's still bigger than 1. So just again, like why I like to do that is so you guys can see it. It's still a stretch, even though it's negative. So it's reflection and a stretch. And then the vertical compression, the vertical shrink. Again, if it's if you have something like square root, maybe it's negative 1/2 square root of x. So again, the negative job is the reflection, the 1/2 job is the compression. If you have cube root, maybe it's 0.75 cube root of x. So just something as long as it's between 0 and 1. Right? Whether it's a decimal or a fraction, doesn't matter. Hopefully none of this is unfamiliar to you guys. Anybody need more time there? Here we're going to do is graph the parent function and then graph its transformation with it, just so you guys can see that comparison. I did intend on these being g of x's here. I didn't get those changed, sorry about that. And the same thing here, I meant these to be g of x's. Here we're going to make a table for the parent function, and then here we're going to do the transformation function. It says compression. Kind of gone back and forth through the years using either word. Doesn't really matter. They're both viable. Vertical shrink or vertical compression, but I know this year I used compression with you guys, so I just wanted to be consistent there. So we're going to look at 1/2 the square root of x. Again, that'll go here. But first, that's one thing about this. The square root function is its parent function first, right? So what does that look like, right? What x value should we use? So since we're talking about square root, we should use our perfect squares, right? We can't square root negatives. So we're going to start with 0, 1, 4, and 9. Don't need that box. We'll just put 5 boxes because similar graphs need 5, so I need 4. So of course, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So I'm going to go ahead and plot those points. Go ahead and draw that graph in. Again, no arrow on the left side, just an arrow on the right side. And I guess while I'm here, I'll go ahead and do the domain and the range of that guy. So that starts at 0, goes to the right forever, starts at 0, goes up forever for the range. So left to right, low to high. So what we're going to see for g of x is we're going to use the same x values. Like, what numbers do I want to plug in to get the square root of? We're going to use those same x values. They're still the numbers that are easily square rootable. But to get to the y values, or the f of x values, or g of x values, what we're going to do is just take those values that we found over here, we're just going to multiply them by 1/2. So 0 times 1/2 is 0. 1/2 times 1/2 is 1, or 1 times 1/2 is 1/2. 2 times 1/2 is 1. 3 times 1/2 is 1.5. So that's what this does, right? It just takes those y values, and we plug in the x, square root it, and then we take half of that. So it's taking the y values and it's shrinking them, it's compressing them. So that's why we use that language, that these values here are now compressed to get these values. They don't move as far. So that's where we get that idea of shrinking or compressing. So this is actually kind of a little bit of a pain to graph because it is so flat. The numbers are so small. 0, 1, 0, 0, all right, and then 1, 1/2, and 4, 1, and then 9, 1.5. And see, those points are really low, really like tight against the x-axis. So this is a very, very flat curve. Yeah. So as we squish it down, it doesn't curve as much anymore. Like I said, you can really see that vertical compression in play. It is flatter than it was before. So, but as far as domain and range, right? The domain didn't change. It still starts at 0, goes left forever, or goes to the right forever. And then as far as the range, that also didn't change because it still starts at 0 and goes up forever, just slower. So compressing it didn't change its domain or its range. But do you guys see how the y values are all half of what they had been? Okay. That was at 1, now it's at 1/2. That was at 2, now it's at 1. That's at 3, now it's at 1.5. That's why we use that language, compression. Anything there you guys want to talk about? Anybody need more time there? Yeah, Peyton, there is. That's why I wanted you guys to pick stuff up. You could do it on DocHub if you want. You could try to draw your own. If you have any of the graph paper from last semester still, you could use that. If you don't have any way of printing stuff. Try waiting until tomorrow and seeing if you could pick stuff up then if we're open. If you really want to try to get it done. Think any of those options will work for you? Okay. All right, last graph here we're going to do today. So notice here we have g of x is the -3 cube root of x. So do make sure, when you guys are doing your homework, that you're really paying attention to what the function is, right? That it's square root versus cube root. Okay, it's a little detail, right? Square root versus cube root, because that will change our x values that we're going to use. The cube root has more possible entries because we can cube root 0, but we can also cube root 1 and 8, and cube root -1, -8. So again, just using those same numbers that we were using on the other side, those perfect cubes. Again, those same values. Cube root of -8 is -2, cube root of -1 is -1, cube root of 0 is 0, cube root of 1 is 1, and cube root of 8 is 2. So I'm going to go ahead and just plot those points. See that same S curve that we saw on the other side. Just that one wrong. Oops. Struggle. Go ahead and draw my curve in. I guess while I'm here, I'll go ahead and talk about the domain and range. You can see that left and right arrow. So this goes to the left forever, goes to the right forever. We can plug in any number we want. That's basically what that means. And it goes down forever and up forever, which means that eventually every number would also be an answer. So we can plug in any number we want and also get every number back as an answer. So if I want to go to the transformation, we're going to use the same x values that we use. That doesn't change. And so if we use that idea like we did last time, if I take those x values, we can just multiply them by -3, because that's what's happening to the, right? We're plugging in our x, cube rooting it, and then we're multiplying that by -3, just following order of operations. So I'm just going to take all those x values, multiply them by -3, and that'll give me my, or sorry, I'll take my y values, multiply them by -3. That'll give me my new y values. So -2 times -3 would be +6. -1 times -3 would be +3. 0 times -3 is 0. 1 times -3 and 2 times -3. That's why it's good to know those parent function values, okay? Or at least the x side of it. Okay? And once you know the x side of it, the y side is easy to find, and then you can use that parent function to help us find the transform function, just straight multiplication. Okay? So go ahead and plot those points. One -3, 8 -6. -1 +3, -8 +6. So you can see now the reflection in action, that the right side was on the top, now it's on the bottom. It's been reflected over the x-axis. Now the left side was below the x-axis, now it's above the x-axis. It's been reflected over the x-axis. You can also see how much taller this graph is compared to the last one, right? It's much higher. That's that stretch in action. Okay? So these are very, very visible changes to the graph. The graph is much taller and the graph is upside down. So as I go to draw it, I can draw a more stretched out version of this S. A lot of curvature here, and close to 0 and 1, and it shoots off down into the right. It's going to curve fast around 0 and -1, and then it's going to shoot off pretty straight, but still should be a curve. But let's head off towards -8, 6. But as far as the domain and the range go, we still see that it goes left forever and goes right forever. That didn't change. So, and we still see that it goes down forever and up forever. That didn't change. So reflection, stretches, shifts, anything like that will not change the domain and the range of cube root. It's always going to be all reals. Anything you guys want to talk about there? Is it making sense how I'm taking the y values from the parent function and getting the y values for the transform function? Is that making sense? Anybody? Hello? Hello? Hello there. Who's awake? One. I've got one. Sweet. All right, last little thing here, just looking at a function, seeing how it's been transformed. Again, definitely something you guys have done before. So we have our parent function. I'll compare that to our transform function. So all I'm noticing is there's a 5 now. And 5 is bigger than 1, so that's a vertical stretch. We use that phrase by factor of. Hey, what's up?
Guess what? I put the Lego set leg at the front page. I made it the way it was. Can I show you?
Sure.
I'll bring it
Okay. And next one. So remember that the negative and the 1/9 do two separate things. Okay? So we refer back to them at separate times. So the negative is doing reflection. So you can say vertical reflection or reflection of the x-axis. I prefer reflection of the x-axis. And the 1/9 is less than 1, so that's a vertical compression. Again, by a factor of. Okay, so just make sure you separate those two things in your head. It's not negative 1/9, it's negative 1/9. And they do two separate jobs. And again, tomorrow we'll add in the shifting left and right along with all the other transformations we already talked about. So that'll wrap up this portion of this unit. So, any questions there on those last two? You should have a worksheet in your Google class. There's a daily point up there. It's open till 4. And then there's the spot to turn in your homework tomorrow. Should all be set up already in Go Formative. So.